let's make a
So
recording.
Okay, I understand that I'm being recorded.
Sasha, make this automatic, the recording.
But
Please.
it's not possible.
Why it's not possible?
Because Zoom doesn't let me do this.
Okay.
So you have a very special Zoom then.
It's CNRS Zoom, you know, it's very special. CNRS Zoom.
So as we're still on this slide, then I can draw in red the claims that were made in my slide so far. So the real thing that I wrote is this, that if you are computably random, you do not imply this. So you can be unpredictable, but not unpredictable. So this is strict. In fact, basically exactly the same proof, we will get this. Because in our construction, when we thought together about something which is computably random, a very low Kolmogorov complexity, it also worked with partial computable martingales, something of and this is what I will need for my proof, that you can diagonalize for a very long time against finitely many players. That also works for this randomness notion. So basically, the proof that I will give you today is good for this or good for this. It's irrelevant. So it will show these two non-implications. Okay, so now should I try to share?
Okay, then I stop sharing. So it should be stopped now, yeah?
And still tells me that I cannot. No, okay, now it's okay. Okay. So
yeah, we can see it.
These were my slides from last time. So I told you what unpredictability was. And we had discussed that you can make something of very low complexity by diagonalizing against all players, but one at a time for a very long time. So you start, if you know if you know a player which is total, then you know exactly how to defeat this player. So you defeat this poor player for a very long time. Then you allow after a while, a long while, you allow a new player to enter the play, and then you treat them as one player, and then a third player and a fourth player. Again, if these players were partial computably random, well, you try to defeat them as long as they play. And if you see one of them at some point stops playing, you just record this fact, and then you ignore this player from now on. Because when a player fails to bet on one bit, this player is out. He's not allowed to, or she is not allowed to continue playing. So basically, it's the same proof. There's still a slight overhead, and we'll come back to that, but for the partial computably random, because you still need to know which players are still betting. So it costs a tiny bit more Kolmogorov complexity, and that is unavoidable. That actually is Merkle's theorem. You cannot get something with partial players in logarithmic complexity. So this is the interesting bit by Merkle. Anyway, that's not very important for now. Just the idea that you can defeat finitely many players by diagonalizing against them for a very long time. Okay, so that's what we got. So if they're partial, it's log n times log n, if you want. Okay. So once again, I wanted to stress the important points of the proof that I will need later on, that really the new players, we decide when we want to introduce them. It really does not matter. Like there's a lot of robustness. We allow, if we want to add them like exponentially fast or non-computably often, it's completely our decision. It will give you something. And at each stage, of course, when we play against finitely many players, what we're really doing is we're building a computable sequence. If for some reason no other player was going to ever enter the game, then the sequence we would build in the end would be computable. So of course, then it would not be computably random, because of course we're only playing against finitely many players. So another player watching that could guess the sequence, right? But if somehow while we play against finitely many players, it looks like we're building a computable sequence, which is another way of saying it has logarithmic complexity.
So we construct a sequence, and there are some important moments which can be postponed as far as we want, and between this moment, the sequence is computable. So if some moment never happens, then the entire rest of the sequence will be computable.
Right. So when you put the two together, the take-home message is that you can decide to look computable as long as you want, and of course you even know the index of the computable set you're making. But that's not really relevant. But
yeah. So the complexity of the algorithm that computes the sequence increases, but it increases. But at each time it increases somehow, and then you can follow it as long as you want. Until the time when complexity is small, and so on.
Indeed. Okay, so randomization. Now we've talked a lot about it. So what happens if we allow a probabilistic gambler? So again, the question is, do we get a strictly randomness notion, and how does it relate to Martinov randomness? So we've already spoiled the answer to that question. So it will be it will still be much weaker than Martinov randomness, but it will still be a stronger notion than computable randomness. So we've also discussed that it was first studied by Buss and Minnis. So they started this study, but they asked the probabilistic strategy to reply with probability 1 something. And then what you can just do is we went over this last time, right? That you can look at the expected martingale. It's just a martingale. Okay, it's real valued when I talked about martingales to be rational valued, but the definition of computable randomness is robust. You can consider real valued martingale or rational valued martingale. It doesn't actually matter. So the expectation is a computable martingale with real values. But that's still, and because of Fatou's lemma, then we get what we want. Okay, so now we remove the Buss-Minnis assumption.
But before we go in this, if it's not total, then we don't get a martingale, but I think we still get a super martingale, yeah?
That's correct.
Computable or not?
Right, but yes, that is correct. But these are equivalent to Martinov randomness, so it's a completely wrong direction to go into because
but this shows that Martinov randomness sequence will be safe under partial computable martingale.
Yeah. I mean, there are many ways to get to that result. Yes, but that's one of them. Okay. Yes. Yes. You're absolutely correct. So that's our claim. Now there is an X which is unpredictable, but for which there is a probabilistic strategy which succeeds to get X with probability 99%, and is total with probability 99% as well. Okay, so that's our another take-home message is probabilistic gamblers do better. And I think this is where we almost stopped last time. So for that, we're going to use one genericity, and one genericity we had defined as the analog to randomness, but for Baire category. And we're going to apply that notion of genericity, which is a topological notion. We are going to apply it to a very weird space, which is the topological space of martingale. And you can think, if you want to think of it topologically, it's just a martingale is just assigning a value for each sigma. So it's a list of values basically, right? And so you can see it as a closed subset of the Hilbert cube with the usual product topology. Or if you prefer to think about this, you can take this metric that I just drew. It's like martingales are close, and then you give more importance to smaller strings basically, and that makes a distance, and that's the distance that describes the topology on the Hilbert cube.
So convergence of martingales is just convergence on every finite sequence.
That's right.
Pointwise.
Yeah. So that's a metric space, very nice. And when we have a metric space, we can do computable analysis. So that's very pleasant. And we can talk about genericity, no problem. It all works very nicely. All right. And so
the definition of genericity is that if there is an effectively open set, we either are in this this generic sequence should be either inside this set together with some neighborhood because it's effectively open, or it should be outside the set with some neighborhood, which is not, of course, not.
Yes. So that's our definition of genericity. We say that in a most general sense, when we have a metric space. And probably you can do interesting things in computable topological spaces, even if you don't have a metric, but you probably need some assumptions that I leave that to the computable analysts to figure out how much you need, how many axioms you need in a non-metric case, but we are in the metric case, so we're safe. So we say that the point is one generic. For every effectively open set, either your point, oh, and I forgot to fix, I knew I had a typo. It's Z again. Z is in U, or Z is in the interior of the complement of U, right? And these things exist because
now we have a problem of connection. Okay, everything is broken. The connection. No. Wow. So it's a problem on Laurent's sides, or everyone
Yes.
hears okay, but just me.
Yeah. So Laurent's side.
No. Okay, so the dilemma, I think, is that, for example, for sequences, we also have this notion of genericity. And the sequences, generic sequences, are somehow opposed to random. They are never random with respect to a computable probability distribution. And
so may I ask if I just want to understand the topology on martingale. So we just take in each coordinate just an ordinary topology, and then we take the product topology.
Yeah,
right?
yeah.
So
just to have an open set, we can fix some number of coordinates, and we write some open restrictions on these coordinates. And this is an open set in martingale space. And this is the same as this metric space. Yeah. So
I seem to be back.
Yeah.
But you lost me for a while. Yeah. I'm sorry about that.
So we stopped at the point when we considered an open generic point in a constructive metric space in general. But if you explained how to construct a generic point with probability 1, that's what we missed completely.
I did not go that far. So this is what we're going to do. We're going to show that indeed, so these things cannot be built computably deterministically, but very surprised, again, to me, this is one of the most striking theorems of computability theory, is that you can actually build these things probabilistically, which is very weird because, again, randomness and genericity are, in fact, there are many theorems that show that they have nothing to do with one another. And I said, like, I think that I told you last time that, for example, if you have a one generic, it is not random, but it cannot even compute a random ever. It is so disorganized that Muchnik would say that it's so organized, in fact, because Muchnik called a one generic a lawful sequence. That it has so much kind of like, it obeys so many laws that it cannot be random and not even be made random by any computable transformation. So it's very strange that you can obtain generics at random. But okay, we can. And I'm going to use what I call a fireworks argument. And I'm trying to push this terminology, and I take it after, so that the technique itself was invented by Klaus, like a while ago now, like more than 30 years ago. But really I knew the proof, but the proof was very strange, and it was a kind of the usual finite injury type argument you will find in computability theory. And it was understandable, but still a bit of exactly what was happening was a bit obscure. So the first time I truly understood the argument was after I talked to Sasha and Peter Gatch. So that was in 2012. So I think the paper that came out of this actually does not have Peter on it. It's Rumiantsev and Shen. the reference. But they use an interesting analogy, which is the fireworks shop. So let me say why we call it a fireworks argument. So we are in a fireworks shop, and here is the problem. So the fireworks in your shop are very cheap. So because they're very cheap, you say, well, they're so cheap that it's suspicious. You know, maybe some of them are defective. And of course, we want to buy, you know, for the party we're going to have tonight, we want to buy good fireworks. So, but because they're cheap, we can ask the owners to test a few in the shop. Well, maybe outside the shop to not set the whole shop on fire, but let's say like in the garden of the shop for safety. And you can test a few before buying one to take home.
So we want to just buy one to make clear.
Just want to buy one good box. One good box. Actually, probably if we wanted to buy n good boxes, they would kind of do the same thing. But so our goal, at some point you say, okay, I think I've tested enough and I want to go home. I will buy the next one. So that's a win for us. Or at some point, we get the owner to fail one of the tests because then we get to sue him, which is a win for us. Again, this is a joke that works better in the United States, because of course, if it happens to you in France, then it's definitely not a win for you. But let's say that in the United States, maybe there is good money to be made in the second case, that at some point you see that the fireworks is defective and then you win the game. Where you lose the game is if at some point you're satisfied with the positive results of the test, and then you say, I take the next one, you buy it, you go home, and that one is defective. This is the case where you lose. Okay, so that's the game. Of course, you have no deterministic strategy to win, because if you announce your strategy in advance, you say, oh, I'm going to test the first 5 and I'm going to buy the 6th one. That's your strategy, if they're all good. Well, the owner is going to give you 5 good ones to test, and it's going to very sneakily give you the bad one when he knows you're going to leave. So no chance to have a deterministic strategy. But you have a very obvious probabilistic strategy, which is to pick the number of trials basically uniformly at random. So if you have like n boxes in the shop, you pick a number that you're going to test at random between 0 and n, right? You test the first k, and then you buy the next one. If all the tests are positive, they all work. Okay, so that's your strategy, and it's a very good strategy because there is basically only one bad case, right? The only bad case is when the first bad box, if any, is exactly the position that is exactly the k+1 for your choice of k, right? Because of course, if you have your first bad box and you choose a bigger k, then you're going to find it during the test phase. And if your first bad box is way above your k, then the box you're going to buy is going to be good. So the only bad case is just when you start to buy the box is the first bad one, right? There's just only one bad case. So there is 1 over n+1 chance to be in this case.
So is it clear what the game is?
And this is actually optimal. So yes, please, if you do not understand this, we can go over it because it's
funny, even independent of any random sequences. So there is a game between two players, the owner and buyer. So the owner actually chooses the sequence of fireworks that he wants to show you, and you just it's like von Neumann game. You don't know the sequence, or you know it but you don't know which is bad, and you just select one number, which is k, and then you test the first k fireworks in the sequence, and then if one of them is defective, you win. If the next one is good, you also win. But if the next one, all of them were good, but the next one is defective, then you lose. This is the game. And the explanation was that there is a very simple way to win this game with high probability. Just choose secretly the number of fireworks you want to test, and then whatever the owner does. The bad case is when the first bad one is exactly at that distance, and for every distance, the probability that you guess you are unlucky to be exactly at that distance is 1/n.
The owner chooses the sequence before.
Yeah, basically, we imagine that the owner chooses for each box whether it's going to be good or bad before closing the boxes. So it's kind of it's the owner. We give him more power than just, he just got boxes from a factory or something. The owner decides in each box whether he's going to place a good one or a bad one, and then he closes the boxes and then he lays them in a stack, and you say, okay, now you can try to test them if you want.
And in the case all of them are good, we take the k plus first means n plus first. So so we obtain exactly 1/n plus 1.
Yeah, but actually, it's better to say that there exists k plus 1 if even k is equal to n. So we assume that there are n plus 1 fireworks.
Which is always bad.
No. Just it can be good, but then if we get this good one,
which is always good.
Yeah.
Okay. So there are n plus 1 of them, and the n plus first is always good.
No. Just n plus 1.
They're just n boxes. They're just
but then you should take a random k between 0 and n minus 1 to be more clear.
No, Sasha, to obtain the probability of failure 1/n plus 1, we need to choose k from n plus 1 different options, right?
No. There are n boxes.
Yeah.
Yes. And k,
I pick a
what
number
about
between 0
k?
and n, and I test k. I want to give myself the option. Again, it's really not important for.
Okay. You test k, and k ranges from 0 to n, right?
It can be one of my strategies to test all boxes, hoping that one of them will be bad.
Okay.
I decide that I want to expose the owner of the shop. Why do I say this? It's because if you really want to know the von Neumann equilibrium of this game, this is the unique strategy to be optimal. N/n plus 1 is exactly this strategy. And the strategy for the owner of the shop is to place 0 or 1, but 1 doing exactly what we do, to place it between 0 and n plus 1. If it's n plus 1, it makes all good boxes. Yeah. This is actually at some point I computed it for the fun. It's irrelevant for this argument, but it's still good to know that this is actually the best strategy you can imagine for the buyer, and for the owner is to place 1 bad box or 0.
Yeah, but then you should say that if we test all of them and all of them are good, then we lose.
Yeah, so we lose because we have no more to bring home.
Yeah. So yes. we buy the k plus 1 and then test it, or just we test all, and if they are all good,
then we have nothing else to buy. Yeah. Then we lose.
Still, it's 1/n plus 1.
Of course. So why is it not important? Is because here I just want to. I will be in a case where the shop has infinitely many fireworks. So basically, it will be my responsibility to pick an n, and I can pick this n as big as I want. So I can make the probability as close to 1 as I want. So it doesn't really matter to talk about von Neumann equilibria, because in fact, in the real game that I'm going to be interested in, it will be my decision to find the sample size. Like I can say, I choose the n as big as I want, and then I pick k at random between 0 and n. Okay, so it's really I still want to play the finite game, but I choose the parameter of the game. Okay, so that's what will happen. Okay,
so if we need 99%, we just wait 100.
We take n equal 100. Yeah. But I will need to do that for we're in computability theory. So as usual for computability theory, we want to win. We want to match countably many requirements, right? So for every I now take a list of all the effectively open sets. So effectively open sets, they are CE objects, computably enumerable objects. So I have an effective uniform listing of all of them. So I can really play them all together at the same time. This is not a computable object, it's a CE object. So I can really list them uniformly. No problem here. Right? And so what I want my point to be generic. So I want that for every effectively open set. Either I'm in a WE or I'm in the interior of the complement. Okay, so that's what I want. But there are infinitely many, countably many requirements to match. I want that to be the case for every E. Okay, and every E will give rise to one game, one fireworks shot game. Okay, so how are we going to obtain our Z? Where we're going to basically build it as an intersection of smaller and smaller open or closed balls. Basically closed balls, I guess. I suppose I've already committed my Z to be in a small closed ball of center Q and radius R. Now I have two cases, basically. Either my open set intersects the corresponding open ball, it does not intersect the corresponding open ball. Well, in which case, I can just say, okay, well, then I'm going to make my ball a bit smaller, and then I completely avoid this open set because this open set does not even intersect my open ball. If I shrink a bit my ball, then I will for sure avoid this effectively open set. Or what I call the sigma 1 case, somebody tells me like, well, at some point this intersection will happen. I have this ball that I'm committed to, and this WE will intersect this open ball that I committed to be in. In that case, well, because the intersection of two open sets contains an open ball, I will find a smaller open ball, which is in the intersection of the two. And then I will commit to be in it, and even in the, you can make the radius a bit smaller, just so you go back to committing to a closed ball. So it's basically the same as when you know the proof of bare category theorem. It's basically the same proof as bare category theorem. Like you try to match more and more open set that come your way. You wait for an intersection, and then you take a smaller. So basically, this is what you do.
So if it's not already in the interior of the complement, then we can wait until we find some element inside this, some extension which is in the set, and so set is open with all the neighborhood. So it's
right. And so because we're in a metric space, when you have an intersection of shrinking closed balls, and the radius tends to 0, because you see at each step I'm going to divide it by 2. My intersection is going to be a point, and this particular point is going to be in every open set or in the interior of the complement. So that's basically the same. So
okay, maybe we should stop now for a while, and I would like to ask someone, do you guess what are the fireworks? What is the good fireworks and bad fireworks? So probably someone can already say what it is. So Sasha, what are the good and bad? Or what is the testing of a firework? So we have an initial fragment of the sequence, and we can decide to test it or to buy it. And to test it or to buy it somehow corresponds to two cases in this dilemma. No, I see that it's...
Question is to which case?
So what is testing and what is buying? Just no, it's actually one bit of information, but still, I want to think about this general idea. So buying a firework means that you hope that something is good, and testing is that you check that it's good.
Testing, probably waiting for a ball from WE which intersects our ball.
Yeah, so we have some ball, and testing a firework means that we wait for a smaller ball, for an element of our effective open set in the ball.
Mm-hmm.
And then if it's not there, we are glad. So no. This means that the firework is bad. No, I'm confused.
Yeah, well, okay. So the reason Sasha is confused because of course there is slight imperfection of the fireworks analogy, because of course when you test fireworks, you know the answer immediately, right? You just test it and you see either it goes boom or if it's, so I think why it was called fireworks is because there's this idea that even if you see that it doesn't seem to be working, and that's how people kill themselves on a regular basis with fireworks, you think it's not going to explode, then you go and you check if it's exploding, and then it explodes in your face. But still, yeah, you have to imagine that it can take an arbitrary long amount of time to be good, right? And this is why I call them the sigma 1 and the pi 1 case. Sigma 1 is if something happens at some point, you will know for sure. Like it's a sigma 1 event, it's a CE event, and you wait for something to happen, and if it does happen, you will know it has happened. And there is a pi 1 case, which is bad fireworks, where something will never happen. Like you wait for to see an intersection, but it will never come. So that's like a bad fireworks. It will smoke, but never explode. And you will never know for sure, right? Stay safe. Don't go too close to your fireworks you think is not working. So that's the bad fireworks is pi 1, and the good fireworks is sigma 1. It was a difficult question that Sasha asked because, again, of course, the fireworks analogy is only an analogy, right? So it was not obvious to guess.
Yeah.
Right. But this is why I call them pi 1, sigma 1. One of the cases is, something will never happen, and one is something will happen, and when it does, I will know. So again, I want to stress that these cases are actually very easy. Like if you think of effectivity, the steps that they're making in case 1 or case 2, they're extremely easy steps. They're completely computable steps. One of them is just to shrink my closed ball by a factor 2, extremely simple. In the other case is just to wait to see an intersection. And once I see an intersection, while getting computable analysis, when you see an intersection of the ball, you can effectively find a new small ball in the intersection. You just wait until you see one. You take it, and then you shrink again the radius by 2. So these, the cases are extremely easily handled. What is not possible is to guess in which, this is just a halting problem, right? You're just waiting for a CE process to return. It may return or may not return, and
that's why we cannot construct a computable generic sequence.
Right. If you could magically, and this is how you can construct using the halting. If you know if you can compute the halting problem, then you can compute the one generic with this proof. You use the power of the halting problem to decide in which case you are, and then you find, then you make a computable step. Then you ask your halting problem again, and then you make the computable step. So computing a one generic cannot be done computably because you intrinsically cannot distinguish between these two cases. But if somehow you could, you would be able to build it. And well, you can guess that randomness is going to help us make this prediction, because we're going to reduce it to for each requirement, we're going to play a fireworks game. But of course, again, the analogy has some limits because we're going to play countably many fireworks games in parallel somehow, right? We need to organize ourselves in a way that we can play all these games in parallel. So if I look at one strategy in isolation, so I have to play one for each E. So I'm going to fix a big N. So let's say 2 to the E plus 10, that will be good enough. Right, that's the number of fireworks, the maximum number of fireworks I will test. But again, this is my decision, so I make it big enough between 0 and that. Okay, and so how does the game start, right? So you just start testing fireworks, right? So what does it mean to test? It means like, okay, I test the first one, and I think the first one is bad, right? When you make a test, you're basically telling the owner, I suspect it is bad. So you're making kind of the guess that it is bad. Right, but again, remember, a bad fireworks is a fireworks that does not explode. So it's a CE process which does not return. Right, you cannot stay here and say, oh, now I'm waiting for this, because if you wait and it's indeed bad, then you'll never know for sure. So if you want to play of course you will win this game, but you will fail to play even other games at all because you're just waiting stupidly for something to happen, right? So you cannot just wait there. So you're going to say, okay, I want to test this, but while you test it, you should start doing other things, right? So you just pick okay, you start making your test of your fireworks. So you say, okay, I have this first event. So my event being WE intersect BQR is empty. I guess that it is the case. And I move on. I say, okay, while I'm waiting, I'm going to work on the other games, right? And of course, if this never happens, if it remains empty at all times, then I win, right? It's a case where the fireworks is bad and I am the one saying, oh, I want this test to be made. So it's okay, I will win the game, right? Again, the analogy with the fireworks shop, again, has some limitation because you will never know you have won in this case. You will just win it in the limits, right? At no point will you be like, hey, you know, you win, you get to do your lawsuit. You will never know for sure, but in the limit, you will win, right? So you start assuming you are in the Pi1 case, and then you start moving on to other games, other requirements. So two things can happen. Either you were right, indeed it was a bad fireworks, in which case, again, you win. So you can start doing the other games. You have already won the game for the game number E. The bad case is we were wrong. This was a good fireworks. It goes off at some point. And well, what do we do then? We make a new guess, right? Because we were working on other games. At some point it goes off and we say, okay, now I'm somewhere else in the game. I have another ball that I'm committed to. I'm gonna make a new guess on that new ball. And I continue like this. Every time I make a guess that I'm in the Pi1 case, I start working on other games in parallel. And I do that for all games, right? And every time I'm proven wrong, I count how many times I was wrong. So that's like basically the number of, like, again, in the fireworks shop, it's like how many boxes I've tested. And if at some point I say, okay, clearly every time I make a test, I'm wrong. Like every time I bet fireworks is defective, I'm wrong and it works. Then, this is important. Then if I see that happened to me K times, then I stop everything else I'm doing. All the other games are put on hold for now. And then I wait for my CE event, which is like fireworks going off. I just take the fireworks home and then I fire it at home. And then I have to wait for that to happen. This is the sigma 1 case, because in the sigma 1 case, you'll remember when I'm in this case here, the second case, I need to do something active that I need to wait for an event to happen. And once it happens, then I need to find my ball BQ prime R prime inside this set here. But to find it, I need to make sure that their intersection is non-empty, right? So this BQ prime R prime is something that I can find if I wait long enough. Okay, so this is what we do here for the ETH game. If we've been proven wrong K times, then we enter this stage where we wait to see basically this event here. And then when it does, then we move on here. Okay, so that's the strategy for one requirement. And I play this strategy in parallel for all games, because you see each strategy allows me to go do other strategies in parallel. Except this last step, which says, no, now you really need to finish what you're doing on this game number E before doing anything else in this.
And if it fails, then the strategy fails completely, and our game is lost.
Right, and the failure that can happen on this point number 5 here is like you say, okay, now I stop everything else I'm doing on other games. I wait for something to happen. That is the failure of the fireworks shop. That it could be the case that I just when I started to wait for a sigma 1 event to happen, this is exactly when it will not happen. So it is a bad case of the fireworks shop when I decide to wait exactly at the wrong moment. And then indeed, I will fail to even return anything because I will get stuck in an infinite loop. And this is where we have failure of our, in the martingale thing. This is the 1% failure rate. It's here. It's in the case number 5 when I choose to wait at the wrong time.
Okay, so is it clear or not?
So that's the strategy.
I'm sorry, it is not.
Is not.
Yeah, I'm sorry. I am the one who's sorry.
Maybe you can start to repeat it until the moment when you are lost.
I don't understand what does it mean, item 3. What does it mean that we realized that we were wrong? How do we?
So, but first of all, is it clear what are the conditions RE are? So the conditions RE, what do we want to achieve? This is clear, or not?
Yes.
No, let's see once again what is RE.
So we want
to. Slide.
For example, good to be back to this slide.
Yes, it is clear.
Yeah, and at any point of the construction, we have some ball. So if you think about sequences, which would make a bit easier, then we construct a sequence up to some moment.
But I don't understand even a more general thing. What do we want? So these are conditions for constructing an infinite sequence, which is one generic, right?
Yeah.
Yes.
So we know that there is one. So
we want to construct one with high probability, with probability 99%.
Mm-hmm.
And so for the first sequence, for the first R1, we want to probability error be 1,000. For the second one, 10,000. For the third is 1 over 100,000. And so
do we handle first VW1 and then VW2, or we handle them in parallel?
We handle them in parallel somehow, like priority argument.
Mm-hmm.
R1 is more important than R2. So at some point we decide to do something for R1 and take the risk that we will never return to R2 and fail. But
so I disagree with Sasha's comment. They're not ordered by importance. This is not an injury argument. They're all equally important. We just need to start by one. But in fact, in the strategy, the games have no priority over one another. When game number 22 tells you, okay, now you need to do something, you have to stop game number 1 all the same. So
how do we handle R1?
So we never if we construct a sequence of sorry, it's confusion. If we construct a sequence of balls, we never change our balls. If the balls are there forever.
Yes.
Yeah.
Once we say I commit to staying in this ball, this is a commitment, and I make this commitment because at this moment I was playing game number E and E. This commitment applies to all other games.
Mm-hmm. Yeah, sorry.
When I say I make a guess, and I remember the guess I'm making at that moment. So for example, I'm playing game number 42, and I say, okay, I bet that this is my current ball. This is my current commitment. I bet that I will never see an intersection. I remember this. Then because of other games, I may shrink. But then I remember in that game when the guess was made. So I realized that I was wrong on my old ball, not on the current ball. I said, like, when I made the guess, this was my ball, and then I realized that I was wrong on that particular guess. But in the meantime, my commitment ball will have shrunk because of other games that I play in parallel. So it is not a priority argument in the sense that really all games are equally important. And when the game forces you to do something, then really the other ones should stop no matter what number they are.
And when you test the new firework, now I don't know, sound is bad?
Yes, sound is bad.
Again, the counts have to be.
Yeah, so it sounds bad for Laurent or for everyone?
No, it's my connection who's bad, but I think it's better now.
Yeah.
Yes.
Okay.
Yeah, it's better now.
It fluctuates. I'm really sorry about this connection.
No. It's just fun of having something online. You never know what will happen. You kind of should be.
So let me repeat it again. So somehow our ball will shrink time to time, right? So when we say that we have made some commitment, that means that we guessed that we are in the second case. So the ball doesn't intersect WEI, right?
Right. So that's actually a good case. I think I've made that commitment, right? I'm going to be in this ball, and then I say like this will never happen. Yeah.
But at some time we can realize that actually this is wrong, right?
Right.
And in the firewall terminology, what does it mean?
So the first one is that you were wrong means you thought it was a defective one, but in fact it went off. It was good, right? And then you realize the owner say, no, come back. You see, it was working. And then you go back into the inside the shop and say, okay, no, I bet the next one will be bad. And then you leave again and go to other shops, right? And then it calls you again and say, no, look, it was good again. And then you have to make another guess. So you come back into the shop K times, and every time it goes off, the owner calls you back inside, say, now what do you want to do? Right, and maybe at some point
but
you get
there is a delicate point, because the ball is shrinking because of, so you had some ball, and at that point you said that let's maybe it will not have an empty intersection, and then the ball shrinks, but you look for the intersection with the initial ball.
Yeah, but okay, it's not very important, right? What I want is that, because if it shrinks for another game, that means the closure of my new ball will not be, I want the closure of my smaller ball to be contained, which should be far from the border of the other one. So indeed, I could have said in the first case, you do nothing at all. And then when you make the other case, you make sure that when you shrink a ball, that you stay away from the border completely. And that will guarantee you success in the first one too. I guess I should have said it like that. So I guess in the Pi1 case, you can say you just do nothing at all, and you wait for other games to take care of it for you. It's a subtlety. If you didn't understand what I just said, ignore
no.
it.
So just if you think that if you make a test and you think the intersection was empty, and then if you find at some point that the intersection is non-empty, you just failed. So there is nothing you did with in terms of balls.
Right. Well, if you were wrong, if you believed it was non-empty and you realized that you could have done something, it's too late.
Yeah.
Right. Yeah. So that's just like a fireworks shop. If you say, haha, I believe it's bad, let's test it in the shop and it's good, then that's over. Like, you have lost that round.
Mm-hmm.
Right. I'm just saying, like, basically, indeed, it is true in the game where all the games are happening in parallel. You don't want to have to do anything in the Pi1 case, because you just say, oh, okay, I think I'm right, and then you just walk away from the shop and you want to never come back in the shop again. So indeed, I wrote this because I wanted to. So basically, what you want to say, you will stay away from the border. You promise that you will stay away from the border. So that's.
So in terms of sequences, there is no problem like this. We just
indeed, if you build bit sequences, there will be no problem. But here we're building a topological object, so we have to be very slightly careful. But it's not a big requirement, right? Because in the sigma 1 case, which will happen infinitely often, you can decide to stay away from the border of the big ball by making your smaller ball. This comes for free. You have a lot of leeway in there, so you don't have to worry about this at all. So yeah, so ignore the then just commit to the, like in the Pi1 case, just assume you do nothing if you prefer, because this is indeed better. So yes. So in the topological case, it requires epsilon more work than the bit sequence case, but it's basically the same proof nonetheless. So
yeah, Sasha.
I just wanted to ask, so like, is it sufficient to construct, I mean, in terms of the argument, like construct a good sequence of balls for one RE, and then since if we have a decreasing sequence of balls, and if we like decrease some of them even more, then this sequence is still good.
No, we never. So we don't decrease the balls which are already declared, I guess.
I mean, so I just want to like separate the argument into two parts and to see whether it's possible. So the first thing, let's say we have some fixed effectively open set, and our goal is to construct using computably, but using randomness, a sequence of decreasing balls such that either from some point one of them belongs to the open set, or at some point one of them is disjoint with the open set. well, in general, we want that for every E, right?
Yes.
Yeah. So the question is more or less, what will happen if we have only one requirement?
Yeah, I mean, so, okay, let's see, we will show that, let's see, assume that we can show this. And then we can say, okay, so we can start do this in parallel. And so like if by taking intersections of all the balls of all the sequences that we construct, and they still work for every E because the smaller are balls, that it doesn't matter.
Yes.
So there is some external interference from other RE.
Yeah, I mean, you can just imagine that you are constructing a sequence of balls for every E. And then you can, every time you get a new ball, you just take in the intersection of your current ball and something inside.
No, that's important.
This is a bit dangerous to view it like this, because of course the sequences of balls you build for different requirements could not intersect, and then you would not know what to do. So it's important that all games happen on the same ball that you're. So indeed, your ball is shrinking, as Sasha is saying. But you may have.
If we buy something, then it's important thing that if we know that something is intersection is non-empty, then we cannot shrink. If somebody else shrink the ball at this moment, it will distort this property. So when we decide that intersection is, we bet on the fact that intersection is non-empty and find an element on this intersection, at this moment it's important that no one shrinks the balls for us. Not for us, but in parallel to us. But while we think that the intersection is empty, then of course they can shrink whatever they want. It's not a problem.
Yes, that's a good point. This is why you cannot have, then you really need to stop other games, because you can, yeah, if you look at one requirement, you can think of other games as shrinking the ball for you when you don't necessarily want to. And that would be bad for the sigma 1 case, because in sigma 1 case, it's very important to make a new ball in the intersection. And if there was a malicious external force that was shrinking your ball, it could, this ball may fail to be in the intersection. So you really need to wait it out on this game. Otherwise it will fail.
And stop doing anything with other.
And you need to stop the other game. You need to put the other games on hold. Say, stop bothering me. I really, really need to be in this intersection.
But if the stop is permanent, that it means that you lose the game against this, which happens with small probability. And combined all the probabilities with the union bound, they have small total probability. So this is not dangerous.
Indeed. So to summarize, so just like in the fireworks shop, the only bad case where we lose is when we exactly decide to wait when we are in the pi1 case, when in fact we decide to say, okay, I have seen k times that I could have taken a ball in the intersection. The intersection was non-empty, and I could have, if I had been smart, taken a ball in the intersection. I've seen that to happen to me k times. I am now going to wait. I think, okay, clearly I've been proven wrong k times. So this k plus 1 time, I'm going to be right, that it has a non-empty intersection. And then we put the other games on hold. And just as in the fireworks shop, the probability to fail is 1 over n. So our n here is, I said 2 to the e plus 10. So for the game number e, we win with probability 1 minus 2 minus e minus 10, which is, if you sum over all e's, you get 99% success.
Okay, so Sasha and Kola, is it convincing or not? Not really.
It is actually. I mean, not with 100%, but
no. There is
99%.
Yeah, there is actually
99% is good.
One small thing which can be confusing, because somehow this game is changing in the middle, because there is no specific sequence of balls which will be tested, chosen by the owner. So somehow, while the other things are shrinking the ball, when we make the next test, we make, I don't know, 3 times we make the test, and after what will be the fourth test is not determined at that moment.
Yes, indeed. The box that we were in, so good point. In the shop number E, the boxes that we actually test in the shop depends on what happened in the other shops, right? But it will depend only on the parameters that we've chosen in the other shops. So that means if you fix all the parameters of all the other shops, the sequence of boxes that you will test in shop number E will only depend on your choices of your case in the other shops. So basically, along like it's like the conditional probability. So on that, you can make the same analysis.
Yeah. So if for example in the shop, maybe the owner can choose which firework give you as the next one, depending, I don't know, on the external events, on the weather, on the whatever. But
yeah.
but still
it still doesn't matter.
It doesn't matter because all these external events are independent from the number that you have chosen in advance. So there is some small thing.
Yeah, but
okay, Sasha, is it clear or not?
Yeah. More.
Let me ask again. So our real tests are as follows. We have some finite sequence, and we just check whether it belongs to WE, right? Or not?
The ball intersects to WE, no.
Intersects, but we can't check it.
No, we can wait until it happens. So the test is that we bet that it will intersect at some point. It will.
That it will not.
Yeah.
So we try to find such an intersection. If we find such an intersection, so our commitment is wrong then.
No, but of course we're very happy if it does not intersect. So I say, oh, I bet, like the bet we make is that it will not intersect. And then we walk away from the shop. And if indeed we were correct on thinking the fireworks was wrong, this is when we sue the owner and we win. So we say, I bet this is a bad fireworks. Just make your test, and then while you wait, I'll go away because I have other things to do, and just wait for something that may not happen, right? And if indeed the owner never calls you back and say, oh, look, it was good, then you win for this shop. This is the good case. We're very happy if we don't intersect. That means we can stay away from this open set easily. So this is good for us.
So at that moment, we have a kind of theorem that there exists a probabilistic machine with which probability 99% produces one genetic sequences of bits. This is more or less, you can forget about all the martingales and another story, but this is theorem which is interesting in itself. So as Levin or I don't know, or Vugen or who put it in this way first time, I think it was Vugen. So with positive probability, you can generate a sequence which is not random with respect to any computable measure. So this is a kind of paradox. You can have a machine which produces something unexplainable with positive probability. So it's a kind of why statistics computable. It's a paradox of algorithmic statistics. So you have a device with a real random coin inside, and it produces a sequence. And then we want to explain the sequence by showing some computable measure with respect to which the sequence is random. And even if the sequence is produced by a machine, still with high probability, we get a sequence which doesn't have an explanation, when explanation is a probability measure which explains this, which make the sequence random. Because the output probability distribution of this machine is not a measure, but it's only a semi-measure. And there is no notion for random for semi-measure and all this story.
Sadly.
Yeah. Yeah, okay. So I think it was theorem of Vugen, if I'm not mistaken.
Well, although I think people, when clouds proved that you can build the one generic as probability one, I think there was enough knowledge at the time to also derive that, because we knew that one generic could not be random. I think more or less around that time it was known. So I think
maybe the Vugen result was even earlier. But okay,
It was one of these, competing, like Cold War theorem, where it was proven on both sides of the.
No, 91 is not a Cold War.
It was the end of it.
No, it was in the small interval outside the Cold War. I would
say. It was about the frontier
on the border,
But if it's published in 91, it's a thesis, right? So probably the claim was made in 89 or something.
Okay. No. This is not a question.
It was a PhD thesis of Kautz.
Yeah.
So it's usually assumed that you don't write your PhD.
No. There is no idea of priority argument. Yeah, in another sense. Okay.
Okay. So hopefully you understood this. I will be happy to talk to.
So are there some questions now, or it's all clear or all unclear, or what is happening?
No questions.
No, it's like, if it's
somehow unclear. The only thing which is not totally clear is that in the firework, in the simple firework game, there was like an assumption that the owner chooses the sequence of good and bad fireworks in advance. And here, it's like
allowing the owner to make the choice dependent on some external event, which are still independent of your internal
randomness.
Right? That's exactly, yeah. That's a point which I tried to make, but I'm not sure it's clear. But okay, allow the owner to change the mind in the middle of the game.
The point at which you may be.
For example, imagine that the owner of the shop has the idea that if you went out for a long time, then the next firework he gives to you is bad one.
Yeah.
Or something like this. And these tricks will not decrease your probability of winning.
Yeah, I understand this. I mean, if I got a specific E, effectively enumerable set, then there is some point in this algorithm, when I do all this randomized algorithm, that I can wait for, after my K, I wait for the intersection and I never have it, right?
No, there is some point when you decide that this is time to really wait for intersection. And stop everything else and just wait for an intersection.
And this number depends on the choices of randomness for all the other E's, right?
No, your decision does, when you decide that with this E you will play on the 37th case, and you decide independently for any other things.
Yeah, I understand. So, but there is some number at which point, if you choose this case, then you will fail.
Yeah, but when
this
exactly
number
you will
independent of the randomness that you use to generate your case, right?
Yeah.
And it depends on the random choices of all all the
other ones. All the games, yes.
Yeah, the exact moment you met the 37th bet when you buy this thing will depend also all randomness on other randomness.
And
but
since
the
it's
number
independent, the same
dependent in
analysis.
Yeah.
Yeah, now I understand.
Kind of. No, you can just use an induction to get a probability of winning after some moment. If you don't, it's just a game. You don't need to decide that the strategy of the other player is fixed in advance. It can change in the middle.
Okay.
Okay.
I will continue because I will not be able to continue next week. I will be in a conference, so I need to finish. Finish, but I will have. Today has to be my last talk, so before a while at least. So
no,
anyway,
but there is a talk about Barnpalais, so it's not the next week, but it will be the other week. Some later.
We'll discuss that.
Yeah,
I will give another talk. I said maybe not so soon. Okay, so we can build one generics with positive probability, and if this was not clear, yes.
Oh, sorry. I have a question. We know how to build one generic. How can we build a probabilistic betting strategy that satisfies a condition?
That's exactly what will be explained now.
Okay, sorry, yeah.
Because now I view betting strategies as just martingales, and I view them topologically as points in this complicated space, which is like, again, like when I put this distance, basically it's a closed space, it's a closed subspace of the Hilbert cube. So basically I have the topological view now, and maybe it will make it even more confusing, I don't know, but let's just see. So now basically what we know now is we have a probabilistic way to obtain generic objects, and this fireworks technique is extremely powerful because it allows you to get one generic object in any metric space you want. So this is, again, to me, this is absolutely mind-blowing, and I'm free to say this because I have, I did not participate in proving the theorem, and I did not participate in making it so beautifully clear. The second part is Sasha's and Peter Gatch's responsibility. So it's incredible. But yes, we can build generic objects in any topology metric space we want. So now, if I think of martingales, they're just objects in my abstract spaces of martingales, and I have a probabilistic way to obtain so one gen here is one generic martingales. I have a process which with some probability greater than 99% will produce a one generic. And actually it will never produce an object which is not one generic. What it may fail to do is to produce an object at all, because in the fireworks, sometimes you get stuck in the loop. You don't produce anything, it's just you get stuck, right? So you have a process which either produces a one generic or doesn't produce at all. So it has some probability of giving you an object. If it does give you an object, this object must be one generic, right?
Yeah, but giving an object is just producing the ball which goes to
a point.
Yeah. At some point they can stop to making the ball
right.
can stop
and
to
from
decrease,
a sequence.
And
basically the definition of computing a point in an abstract space is to be given such a sequence of balls. Basically, for example, we say that a point in a complicated metric space is a computable point. So you can think of a computable continuous function, or you can think of like a computable triple of reals or something. Like the way you say like this point is computable is like you have a computable sequence of balls. So computing a point, because of course you have to give a representation of a point when the space is too complicated. So basically the notion of a point in an effective sense is being given a decreasing sequence of balls which converges to it, right? But what I want to stress is, okay, now it's not a probability measure, this psi, because there is also a probability of not returning anything. But when your algorithm returns something, then it's always one generic. Okay, so it's not a probability measure because it has a probability of failure, but it still gives full measure to the one generics. This is what I want to say. Right? So it's a push forward measure, which is not computable and not a probability measure, but it's still a measure.
But
so you can
still with positive probability, you still get a sequence of balls. Just the sequence of balls stops somewhere that you don't have an
right.
So
and
the
that's
first,
not really
if you get the first 100 balls, it doesn't mean that it's defined. It may be still undefined, which means that at some point it will stop shrinking.
Yeah, but I mean, in terms of generating a point in the space, the target space, you're not doing that. You're failing to specify a point.
Yeah,
you're specifying a neighborhood, but you're staying fuzzy about the actual point. So that's what's happening. Okay, so now remember that in our construction of something which was unpredictable, we said we could follow something computable for a long time. So for in a construction of a particular unpredictable X of low Kolmogorov complexity, we said, oh, we can look computable for as long as we want. Okay, so let's just say like for the moment that we had a computable binary sequence, which I call CE. I claim that the set of martingales which achieve capital E at some point while playing against this computable sequence is an effectively open set, which is dense. Yeah, I didn't write effective, but it is effective. The effectiveness will also be clear. So why?
So for every martingale, you can find a close martingale which is winning.
Right. So suppose you have an open ball and you want to show that in this open ball there is a martingale which achieves capital E at some point on sequence CE. Well, we discussed, I think last time, that if you have a computable sequence, it's very predictable. Namely, there is a strategy which always bets all its money on the next value to be the value of CE. You can compute CE, you know what CE is. So if you know CE is 0, 1, 1, well, the first time you bet all your money on 0, the next time you bet all your money on 1, the next time again you bet all your money on 1, you can just play the doubling strategy. So if you really play on that computable path, then each time you double your amount of money. Anywhere else, you lose everything, but that's okay. As long as you're playing really against this computable sequence of bits, then every time you double your money. So I call that doubling martingale HE. And well, my space of martingale is not just a metric space, but it's, let's see, it's complex, right? I can make any linear combination between the center of my ball and that martingale HE. So I can take if I take lambda small enough, I will enter the ball. Okay. This is basic analysis. Yeah. So I have this martingale D prime, which is a mixture of my original D, the center of my ball, and the doubling martingale HE. How small is the lambda is not my choice. It will depend on the radius of the ball. It might be, I might have to make it very, very small, but it doesn't matter because in this martingale D prime, it still has a bit of HE in it with some positive lambda. So that means that when I play against the computable path CE, my capital at stage n is at least lambda, which is how much capital I saved to play my double strategy, times 2 to the n, because when you play the doubling strategy at stage n, you win 2 to the n. So lambda is out of my control, but I can play as long as I want. So at some point, no matter how small the lambda, there will be an n at which point I win.
So there is an important thing. So the D prime is close to D in the space of martingales, but this doesn't mean that it's close everywhere as a function. For long sequences, the difference can be high, and this is why D prime can win while D lose something. So we just need to construct a close martingale. It's enough to be able to construct it close on some finitely many numbers. And if it's we just need to save at least some money up to this point on our sequence, and then having this small amount, we can go high starting from this point, and this will be a small change in martingale.
Yeah, so if you want to have a more dynamic, if you don't want to have a topological view, yeah, you can think of like you're playing some game, or some gambling game, and at some point you say, okay, maybe it looks like this sequence might be CE. So you just set a microscopic amount of money on the side, and then you give it to some friend, and you say, go with this lambda amount that
it's
I'm
all
giving
clear.
you.
It's all just continue.
Yeah, okay.
I think.
Okay.
Yeah.
I was trying to
okay.
explain this. Okay, so if it's so clear, so good. Happy to have that. So it's it's dense, right? Because for some n, if you put the quantifier n, there exists n such that you win capital E. Then, well, if I have a one generic strategy now, I need to meet all these dense open sets. So that means that for every one generic, right? If you're one generic, you must belong to every dense effectively open set. So for every one generic G, there must be an N such that you achieve capital E while playing against CE. Okay, so that's one thing, but this is point-wise. This is true for every G, there is an N. But okay, remember now that we have a measure on the set of generics, right? So if for every point there is an N, that means that there if you fix any epsilon as small as you want, then there must be a big N such that for most generics, they achieve capital E before this big N, right? Because for each G there is an N, then there must be an N such that almost everyone wins before that. Right? Which is that's a union also. Well, because I know, like, if I take the union of place of G such that for each N, I take the union over N of the D which which achieve capital E before stage big N. If I take the union of all N's, I get full measure psi of S. A full measure of the whole space.
So you are trying to prove what? Just say it again.
That if I take I now have a probability measure on generics.
Yeah, on martingales.
I know that all of them, for all of the generics, they will win more than $E on sequence CE, but some of them fast, some of them slow.
Yeah.
I want to say that I can still choose a late enough stage big N E, such that the vast majority of generics for that measure psi will achieve capital E before that stage.
Yeah, no. So there is some arbitrary choice that you, for some reason, you decided you want to get more than E on E sequence. You can get more than E square or whatever. Just
it could be E square if you prefer.
But it's just we take E. But then when we look how long should we wait, on which level this happens for long and almost with small probability among the generic strategies, generic martingales. Yeah.
So except for a fraction epsilon of generics, again defined by the new measure that we have on generics, defined by the fireworks argument. Except for this fraction epsilon, they all achieve capital E before that stage.
Yeah. But this is non-constructive. We cannot compute an E.
This is completely non-constructive, but our proof of building an X, which was computably random with low Kolmogorov complexity, was very non-effective either. So basically, we're done, right? I go back to my construction earlier, and between each stage where I add a new player, I follow some path CE, and I'm just going to decide to follow it until position NE as defined in the previous slide. What does that mean? That means that a measure psi of S minus epsilon E of martingales will achieve capital E by the unit bound. That means then you will succeed with probability as close as you want to psi of S, which itself is more than 99%. And that's it. There's nothing else.
So this low complexity is a low amount of information about what? When the new NE appears or what?
So we don't care about Kolmogorov complexity at all now.
Yeah.
Right? It's just saying between the addition of players, I follow a computable path.
Yeah.
If I want, I can even compute the index. I don't even need to because it's not effective, but I'm following some computable path CE, which allows me to not make these players win money. And I'm going to decide to continue this, to limit the number of players to this number until stage NE. And only then will I add a new player. And when I add a new player, then I start diagonalizing. I start following a path CE prime, and I'm going to wait until NE prime to introduce a new player. So basically, the decision to add new player now depends on what happened in the fireworks. I mean, the measure induced by the fireworks.
Yeah, but our goal is what? We want to construct a sequence which is not random with respect to probabilistic martingales, but is random with respect to computable martingales.
Once again, we gave a template for the construction of computably random. We just say, add a new player, diagonalize against this finite number of players for as long as you want until some stage big N. Add another player, diagonalize until N prime, add a new player, diagonalize until N second.
And in this way, this is done to get, this guarantees that we are computably random. We are winning against all the computable martingales.
No matter what choice of N prime, N second we have.
And now we postpone the inclusion of new martingale until the moment that with high probability our random generic martingale will win a lot.
Yes, let's say the fireworks, even if you want. The fireworks will give you a martingale which wins a lot.
And so we have a new source of error. Where there was some probability that the generic martingale will not will not appear, but also there will be some source of error when it appears, but we don't wait long enough in our original sequence. And so we combine these two small errors to keep them small altogether.
That's quite right. And so that's all.
Let's see the next slides
for this part. So basically, again, I want to comment that once you have the right tools, this is actually easier. Our original proof was harder than that, but if you really think of fireworks and you really think of fireworks in an abstract sense, it actually gives you very powerful tools to prove what I think would be a difficult result.
But original proof of what?
When we first proved this
so you first came, but it was never this complicated proof. Fortunately, was never published or
it was still fireworks based, but it was more like ad hoc instead of having this completely abstract viewpoint like topological.
Okay.
Anyways, so now we have this new notion, which is AEM predictability, and as we discussed, it's implied by Martin-Löf random, but could it be so strong that it is in fact Martin-Löf randomness? And we that not at all, because in fact you can still build something. You basically have to make a construction like the diagonalization against deterministic ones, but you also add a bit of information to approximate your probabilistic strategies, and you can more or less manage to make that extra amount of information small, so you can continue. You can still maintain the logarithmic Kolmogorov complexity.
Oh, but how it's possible? Even with
partial.
It seems that even with partial computable martingales, you have just a bit bigger than O of log n. So why don't we have this bigger number here? Okay, there is again a connection problem.
Саша, здесь не это. Здесь я думаю, что total.
I missed your question.
Сюда определенное.
Okay, so if this unpredictable, almost everywhere unpredictable sequences should be random with respect to partial martingales, no?
In this theorem, do you consider total or partial martingales?
So, in this theorem, it has to be total martingales on the left side. Because, and this is where it gets interesting, is if you have a sequence of Kolmogorov complexity which is logarithmic, then it can be predicted by partial martingales, even deterministic ones, and this is Merkle's theorem. If your sequence is too simple, then it can be predicted with the price of being partial, because we know that total martingales are very, very weak. There's no, basically, you can never be so simple in terms of Kolmogorov complexity that you'll be predicted unless you're completely computable. So this
and
is actually
if you allow
a
partial,
separation.
if you allow partial martingale, you still have the theorem, but with just a bit more here in the logarithm term, or
yes, I think we can. Yes, so if you allow partial, I think we can get something of small Kolmogorov complexity too. Yes,
yeah.
but I think something like log n times something. I can't remember exactly, but yes, we do get the separation as well.
Okay, so fortunately we don't get a new open problem which can be open for 30 years, like comparing this Muchnik unpredictability and Martin-Löf randomness. So in this way there is no clear conjecture how to get Martin-Löf randomness.
No, at least there is no. I mean, of course, you could also look at the probabilistic version of
non-monotonic
thing, and then
but then we already don't have.
But already we do not. Yeah.
But we have only separation in one direction, right? Not in the other direction.
Yeah, that's quite right. Well, well, actually, it depends. If you think of at least a comparison between AECR and PCR, now with this theorem, I've given you both directions.
Which theorem?
Well, with we first constructed something which was partial computably random, so partial deterministic strategy which could be guessed by probabilistic strategies. This is
right.
And this theorem gives you the other direction. I have something which cannot be guessed with probabilistic total strategies, but which can be guessed with partial deterministic strategies. So I know, I'm sorry, it's becoming a bit convoluted.
And is this the old stuff, or just also?
Oh, this is also in our paper.
I see.
Yeah, so we have a full separation.
Okay.
Well, I mean, we proved this blue theorem, and the fact that the right-hand side implies not partial computably random. This is Merkle's theorem, which is very useful for us.
Yeah. Okay.
So basically, the idea is whether again, like we haven't done so because, well, we're lazy, but there's a whole slew of randomness notions you can make, and some of them you could make probabilistic. And the question is, well, do you always get for some notions, if you look at the probabilistic version, like Martin-Löf random, you just get the same notion, it doesn't change anything. But we have exhibited notions of randomness such that if you look at the probabilistic version, you get something else. For example, Schnorr random, it also follows from what I presented, that Schnorr random, you get a different notion if you make a probabilistic version. For people who know what Schnorr random is. For stochasticity, you get a different notion. So it's interesting.
But is some new class? It would be interesting if some new class introduced by this almost this new oracle thing would coincide with some existing class which is different on this picture.
Of course, so, that would be nice.
Yeah, but this you don't know when.
Oh, it's almost surely not the case, but. It would be, of course, amazing, but it's not likely.
And what about the probabilistic version of Martin-Löf randomness? That's the same, right? Can you hear me?
It's the same because of Van Lambergen theorem.
Oh yeah, okay. And I have a weird question. So on your slide 27, you had this function n capital subindex e, something like this. Yeah, this one. So did you try to compute it? Is it a computable function, or it's like Busy Beaver?
It's in between. If you want to compute such a sequence, you need to have the power of almost everywhere domination. So I'm like, this would probably take us too far, but basically, if you want to build something which is computably random but not Martin-Löf random, you need to be able to construct a function which grows faster than any computable function. So this is what we call high functions in
okay, then it's very complicated.
If you want to do that here, you need almost everywhere domination, which is a whole theory of fast-growing function, which is in between Busy Beaver and dominating all computable function. It's strictly in between. So it's a fascinating theory of building fast-growing function.
And there is no hope to modify the construction to get it computably bounded, because that would mean that in your strategy, the capital increases computably fast when averaged over all the Martin. So with the expected value of the capital would grow computably fast.
Okay, so here, and because it's late, and
yeah.
Okay, but while you think,
no, but actually I'm wrong. I'm wrong. I mean, my co-authors are here. Maybe NE is just computable, right? Because psi is lower, so you compute. Yeah, but I don't know. No, because I don't know psi of S. I do not know. I want to have a small set of failure compared to psi of S, and that I do not know psi of S. Yeah. So it's not. I mean, I don't think it can be made computable. What I said before, I don't think it's enough to say that the sequence NE cannot be made computable.
But how do you prove that the Schnorr randomness is different in the probabilistic version?
With this proof, actually, because in fact, we not only do we achieve capital N, but we achieve something which is close to 2 to the N. So basically, we have a lower bound also on how fast we succeed. If I want to get better than, I have this lambda times 2 to the N. So if you give me some bound in N that I need to beat, like I don't know, N square, I would also beat it at some point. Like if instead of E I put E N square, I could also do it. So that would also
okay,
you win in a Schnorr way, and even in a stochastic way, you predict so many bits correctly that it's not even church stochastic. It's like you really win with these probabilistic strategies. So it's even church stochastic somehow is not stable under AE. So surprising.
Yeah. Okay. So thank you for the talk.
Thank you for listening. I hope.
Yeah. And so do we have, Kolja, do we have fixed plan for the next time?
No plan. Let's skip the next time, I guess.
But there was a plan to have a talk of Zavgarov, no?
It will not happen next time.
So not for the next time.
Mm-hmm. Let's wait a bit until Zavgarov passes.
Okay. So but maybe there are some other people who want to give a talk, no?
Not yet.
Okay, so by default, the next time is skipped, by maybe someone appears, and then we can send.
Okay.
I can send a message.
And Sasha, please make this recording available to everybody.
Yeah, I'll try. Yeah, I hope it is recorded, but you know. Okay.